Hey, hi everyone. Thanks to the organizers for inviting me to speak here today. I'm going to be talking about some work in progress with Steve Schenker and Shenyu Yao, some comments on wormholes and factorization. So here's the main problem. In conventional ADS-CFT, space-time wormholes lead to the so-called factorization problem, first introduced by Maldacena and Maus. For example, in 2 dimensions, this cylinder geometry appears to prevent what should be products of partition functions from factorizing. So here, these 2 boundaries are thermal circles for 2 copies of the boundary partition function. And we have a geometry which is a space-time wormhole connecting them. These are the geometries that are causing the issue. So perhaps space-time wormholes should just not be included in the bulk path integral, or somehow sum to 0. In either of these cases, there would be no factorization problem. But there are some indications that space-time wormholes should play a non-trivial role. So for other quantities for which there is no factorization problem, space-time wormholes seem to give a sensible answer. And this is even in theories with a fixed Hamiltonian. So the page curve of Hawking radiation and the ramp in the time-averaged spectral form factor are both quantities for which there are indications that space-time wormholes give the right answer. But those same space-time wormholes, when applied to closely related problems, give a factorization problem. So in this talk, we're going to focus on just one of these quantities for simplicity, which is the analytically continued partition function. We take z of beta, continue to beta plus it, with t being time. But mostly, actually, we're going to focus on a fixed energy counterpart, y of t. So how does this quantity behave? For a fixed system, if you take the modulus squared of y of t, it is very noisy at a sufficiently long time. So there's an initial smooth decay, but then this red line becomes very noisy on a region of time which we refer to as the ramp, the reason will become clear in a moment. However, if we calculate the time average of this quantity, we average this noisy signal over sufficiently large time windows, the answer we get is smooth. And in fact, that answer, this black line here, the ramp, is correctly given by wormholes based on our expectations from random matrix universality. So the wormholes are getting the right answer for the average. But how do we, in a bulk description, also capture this noise? So as a rough goal for this talk, we seek an effective description of gravity with something like microstate noise, which captures some aspects of the noise, but includes wormholes. We wanted to include wormholes because we've seen that the wormholes are doing something. So roughly, this is like analogous to something like hydrodynamics with quantum noise, or souped up to include Brownian motion. So going forward, an analogy that may be useful the rest of the talk is the computation of the spectral form factor, this y modulus squared, but in a non-gravitational theory. It's like theory of chaotic billiards. So here in the picture, I have a billiards table, and in red, I have a path of a billiard ball. So for this system, the path integral for y of t can be done by saddle point. We sum over all the orbits of period t to get this quantity y of t. Here, the sum a labels an orbit, and we have the a to the I action. So it's a bunch of phases, and they sum up to give this noisy answer. Now, if we want to calculate the modulus squared, we simply have a double sum over a and b. If we do the time average to get this smooth answer, this double sum turns into a single sum, because the off-diagonal terms of this sum average to 0, leaving just the a equals b terms in the sum. Correctly treated, this sum gives you the right answer, this linear ramp, which we expect based on random matrix universality. So we want to think about this diagonal piece as roughly analogous to the wormhole. The wormhole gives this factor of t, and this double sum, this diagonal sum does as well. So for us, this motivates a cartoon of factorization in ADS-CFT. So what we do is we view the wormhole as a diagonal part of a double sum over so-called broken cylinders. And then to get a quantity which factorizes, we add in the off-diagonal terms of the sum. So here I've pictured some a broken wormhole, and it's got something going on here labeled by B or A, and we sum over something like a boundary condition there. This is just a rough cartoon, but we can ask, is there evidence for this picture in a gravity theory? And we'll find that this is closely related to an effective description for some theories. However, in this cartoon, the wormhole is emergent, not a fundamental ingredient in the calculation. It only emerges when we, for some reason, restrict to the diagonal part of this double sum. And related to that, factorization is manifest in this cartoon because we have a manifest double sum, which is just a square. So now we're going to move on to some gravity theories. And these theories are dual to ensemble averages of boundary theories. This is different than conventional non-averaged ADS-CFT. So in these theories, we can study factorization by focusing on a single member of the ensemble. So for example, we can compute partition functions, where for each partition function, we've chosen the same member of the ensemble. That's just it's simply going to be a product of partition functions, as opposed to the ensemble average of the product. So in these theories, wormholes are fundamental. So it's a bit different than the cartoon we just talked about. So we're going to first illustrate this using a simple toy model of gravity, which was introduced by Merolf and Maxfield. This is a topological theory of two-dimensional surfaces. And this model builds on some old ideas of Coleman, Giddings, and Strominger related to space-time wormholes. Okay, so now I'm going to go through some formalism a little bit quickly in the interest of time. This was all explained in much more detail in the paper by Merolf and Maxfield, if you're interested. So in this theory, instead of computing products of partition functions, what we compute are correlation functions of a boundary operator Z in states of closed universes. So this boundary operator replaces the partition functions. So as an example, we'll look at a special state, the no boundary state. This is like the vacuum state of closed universes. So correlation functions in this no boundary state, like this one, for example, don't factorize. And the calculation for these guys, we sum over all surfaces with these three boundaries corresponding to the three operators in the correlation function. This calculation looks like the computation of what would have been three copies of a partition function. However, in addition to this no boundary state, we can consider other states. We can act on the no boundary state with this boundary operator Z. More generally, we can consider a function of Z acting on no boundary state. When we compute correlation functions in these states, we have to add extra boundaries to the path integral, state boundaries. So here we have a 1-point function of Z and some state psi. And I have a boundary corresponding to the operator in the correlation function, but I also have all these other boundaries which prepare the state psi. And so this red line here indicates that on this side, we're possibly considering a superposition of boundaries which prepare the state psi. Okay, so in eigenstates, which are in this context sometimes referred to as alpha states, correlation functions, of course, factorize. They're simply a power of the eigenvalue of Z. So this eigenstate corresponds to a single member of an ensemble of boundary theories where Z has a fixed value, which is Z naught. Okay, so we can ask, how do correlation functions factorize in one of these eigenstates? Surfaces with many boundaries and hygienists complicate the story. In an exact eigenstate, the surfaces are not suppressed order by order in the topological expansion. On the other hand, if you look in the no boundary state, there's a nice simple topological expansion and these surfaces are small. However, in certain approximate eigenstates, these surfaces are not important and we can ignore them. So if we look at approximate Gaussian eigenstates, essentially this amounts to ignoring effects from the discreteness of the spectrum of this operator Z. And it corresponds to only keeping disks and cylinders in the sum over topologies, as opposed to things like three-hole spheres and so on. So this truncation of the model to just disks and cylinders we refer to as the Coleman-Giddings-Strominger model because of the relationship with its older work. So here I've pictured two wave functions in this Z basis, the eigenbasis of the Z operator. And this operator is a discrete spectrum, which I've indicated with these little ticks here. In yellow, this is the no boundary state. It's spread over many eigenvalues of Z. And thus, it's not very close to an eigenstate at all. However, this black wave function here is an approximate eigenstate. It's sharply focused around a single value of z, z naught, but there is some width to it. It covers many, but not exponentially many, discrete eigenvalues. So in these states, we can study an approximate version of the factorization problem, where the error in factorization is small. It's controlled by the small width of this wave function. So in this Gaussian disk and cylinder approximation, the operator z behaves like the coordinate of a shifted harmonic oscillator. And so it's useful to just introduce creation and annihilation operators like we would for the harmonic oscillator. So we can express z as its one-point function, the disk, plus a dagger. And a annihilates this no boundary state, which acts like the vacuum state of closed universes. So now we can construct what we think of as n universe states by acting with creation operators on the no boundary state. So as an example, if we take the state z to the k and write it in this basis, it's a superposition of states with at most k universes. So here, z squared has a component which is just has 0 universes as proportional to no boundary state because we've capped off these boundaries. It has a component with 1 universe because we've capped off one of them. It also has a component with 2 universes. In this Gaussian disk and cylinder approximation, it's actually useful to think about these correlation functions as overlaps of states instead. So the way we do that is we take this correlation function, write out psi as this function psi of z acting on the no boundary state, and bring these two functions psi from the bra and the ket together. Now we have an overlap between state z to the k and what we call psi squared, which is made by combining both copies of psi of z. So here we have a picture illustrating this. This overlap, which is equal to the 2-point function of z, is an overlap between this unnormalized state and this unnormalized state. This purple line indicates that we might be summing over different numbers of boundaries here to prepare the state psi squared. So now this is useful because correlation functions of z, say z to the k, involve only the components of the state psi squared with up to k universes, no more. And we can see this just by inserting a resolution of the identity in this number basis. So 2 examples are the 1-point function and the 2-point function. So the 1-point function, we sum up our overall surfaces with 1 boundary for z and the boundaries for psi. We have a disk contribution where it doesn't connect to the psi squared boundaries at all. We can also connect the psi squared boundaries with a cylinder. This picks out the 1 universe component of psi squared, which we've represented with this red circle. So just to reiterate, 1 psi squared, this is a 1 universe wave function, but it's prepared by summing over surfaces with many boundaries. So similarly, the 2-point function, where we subtracted the disk for simplicity, involves only the 2 universe component of psi squared. So we can connect the 2 z boundaries with a cylinder, and psi squared factorizes out. Or we can pick out the 2 universe component by connecting the psi squared with 2 cylinders. Here, the linked red boundaries indicate that this is the 2 universe component, not just 2 copies of the 1 universe component. So for psi and eigenstate, factorization requires that the 2-point function is equal to the square of the 1-point function. So the square of the 1-point function is the square of this 1 universe component. The 2-point function is a cylinder plus the 2 universe component. So in this model, the 2-point function has this fundamental wormhole, but the square of the 1-point function, this side does not. So essentially the square of the 1 universe component has to contain the cylinder. So here's just an equation expressing this picture here. So making an analogy with the periodic orbits that we talked about earlier, if we take the cylinder to play the role of the diagonal sum, this thing here, this 2 universe component, plays the role of the off-diagonal part of the sum. This is because if we add it to the diagonal part, it gives us a square. Or equivalent, we can think about it as we take something which was a square and subtract off the diagonal. However, this is a little bit silly because there's no sum, there's no double sum going on. But the analogy is sharper in JT gravity, where there is such a natural double sum. So that's what we'll move on to now. So in JT gravity, instead of a single operator z, we have many operators, z sub I. We can take these to be z of beta plus it or y of t. for different values of t. Y is useful because on the ramp, y of t for sufficiently different t behave like independent Gaussian variables in the no boundary state. So essentially, JT gravity behaves like many copies of this Maralfin-Maxfield model. So we can make universe states by taking y, subtracting off the disk, and then acting on the no boundary state. This will create one universe states t. More general operator zi will create one universe states with a label I. And then the Hilbert space is spanned by n universe states where each universe, 1 through n, has a label. So just to make things a little bit more concrete, the overlap between these one universe states t created by y are described by this cylinder geometry. So here we have a boundary corresponding to y of t, another corresponding to t prime, and the cylinder tells us the overlap.
Phil, just a second. There's a question in the chat, a clarification.
Oh, yes.
What is y? Is the question.
Oh, y is it's a fixed energy version of this z of beta plus it. So essentially, we do like a inverse Laplace transform with respect to beta, or we add in a smooth energy window as well. So this is fixed temperature. This thing is fixed energy, but I've dropped the energy label just for cleanliness.
Okay, thank you.
So it turns out that the disk and cylinder approximation, dropping all these extra geometries, works for many observables in appropriate approximate eigenstates. So here in this model, it corresponds to ignoring the discreteness of the spectrum of the random matrix dual. So we take the density of states of the model to be the leading order smooth density plus some noisy fluctuation, delta rho of E. This, instead of having the discreteness in it, we take this noisy fluctuation to be continuous and Gaussian distributed. So after Fourier transforming, these variables behave like the independent variables y of t. So we can think about those as the random variables for the model. So one thing we can do is, in this approximation, calculate the noisy part of the spectral form factor, this modulus y squared, on the ramp. This is up to a time which depends on the error which we allow. So, for example, if this solid red line gives us the quantity y squared for a specific exact eigenstate, which corresponds to a specific choice of Hamiltonian of the dual theory, we can't get the exact function on the nodes, but we can get it to within some error, which is this fuzzy red part, which is what the error is much smaller than the size of the fluctuations. So our approach is related to eigenbranes, which is a method for constructing exact eigenstates, including the discreteness. However, the gravity computations are difficult to control in these states. So it's useful to define another orthogonal basis. So in the one universe sector, these are states B corresponding to circular spatial slices with length B and zero extrinsic curvature. So here's their overlap. In the n universe sector, we could have many universes, each with some length B1 through Bn. And so, for example, we can use this basis to describe the cylinder as two so-called trumpets glued together. So we take the cylinder and we insert a complete basis, resolution of the identity in terms of this B basis in the middle here. So this is one way of seeing the cylinder as something like a diagonal sum, like we saw in these periodic orbits. So in this B basis, what is the condition on psi squared such that correlation functions factorize? So for general operator Zi, the 1-point function acts like a sum over B. Really, it's an integral. So subtracting off the disk, we can pick out the one universe component of psi squared by connecting with the cylinder. And we sum over the different values of B on that circle. Similarly, the 2-point function behaves like a double sum over B1 and B2. So when we take the 2-point function, subtracting the disks, we can connect the two operators, Zi, Zj, with a cylinder, or we can connect them with cylinders to psi squared, picking up this two universe component. And then we have to sum over the values B1 and B2. So identifying the cylinder as this diagonal sum over B1 and B2, B1 equals B2, by inserting this resolution of the identity, we can write both the 1-point function squared and the 2-point function as double sums over B1 and B2. The cylinder, of course, is like the diagonal part of the sum because we only have one value of B. So when we express this requirement in the B basis, what we need is that the square of this one universe component, we need the square of the one universe component to be the two universe component plus this quote unquote diagonal thing. It's a delta function in B1 and B2. So this diagonal part contributes the cylinder. So here, the two universe component is analogous to these off diagonal terms in this double sum over periodic orbits. That's because what we do is we add it to this diagonal piece and get a double sum which factorizes. So we can ask what's special about this diagonal component in the full many universe description. So when we compute correlation functions, multiple z's in a state size squared, the different z's in the correlation function share all the closed universe boundaries. So here, if we compute a 2-point function of zi, zj, they have the same boundaries that they can try to connect to. So a consequence of this is that they can't connect to the same closed universe boundary with a cylinder at the same time. This would have to be a 3-hole sphere, which is suppressed. So the idea is that if psi is an eigenstate, then psi squared is tuned so that its two universe component almost factorizes, as if these two z's didn't share the same psi squared. They had their own copies. Except there's a correction where we have to subtract off the cylinder, this diagonal piece. It's due to this geometric exclusion effect. So now what we're going to do is introduce an effective model which takes advantage of this simple description in terms of the single universe wave function, B psi squared. So in the full model, the gravity computation involves many closed universe state boundaries, which represent the full psi and psi squared. However, we've seen in the disk and cylinder approximation, for simple correlators, we only need the components of psi squared on a few boundaries, which are just simple functions of just the one universe component. So what we want to do is trade this one universe component, which is created by summing over these many boundaries, for a single dynamical boundary with a random boundary condition. So to be a bit more precise, we can describe this random boundary condition with a random Gaussian function, capital psi of B, with this variance. So capital psi replaces the one universe component, B psi squared. And for an example, the equation for y of t becomes just, we have the disk contribution, which is unchanged. But now we have this cylinder with a random boundary, and this the contribution is this thing here. We essentially glued this to this function psi of b. So for a single draw of capital psi of b, this effective model reproduces the noisy signal on the ramp up to some time and with some error. So now, instead of summing over many state boundaries, we only need a few boundaries. So as an example, for k partition functions, we only need up to k dynamical boundaries. For 5 copies of y, we need at most 5 of these red boundaries. Here I pictured an example contribution. The boundaries can connect to each other with cylinders. I can have a disk, or I can have these independent random boundaries. And just as an aside, we could also choose a different boundary condition for the dynamical boundaries, instead of just this 0 extrinsic curvature boundary condition related to this B wave function. But we're going to stick with this, this choice for simplicity. So if we take the answer for a single y and then square it, and then average over the ensemble, psi of b, we recover the wormhole by gluing together these random boundaries. So for a single y, we have these cylinders with random boundaries. Take 2 copies of it, averaging over psi sets b equals b prime, which gives us the cylinder. However, the gravity path integral for 2 y's includes an explicit wormhole includes this thing and these pairs of random boundaries. So it's like we're overcounting because these pairs of random boundaries are including the wormhole. So by giving up this many universe description, we've given up this geometrical mechanism for excluding the cylinder from what used to be this two boundary quantity. So in order for this effective model with the random dynamical boundaries to match with the full model, we need to introduce an ad hoc modification to the sum over geometries, which we refer to as the exclusion rule. So the idea behind the exclusion rule is to view the appropriate diagonal part of the double sum over dynamical boundaries as equivalent to the cylinder. So this would have been just a numerical equality between a subset of these pairs of random boundaries in the cylinder. Now we're elevating that to something, to an identification. And in the sum over geometries, we include just one or the other. We don't want to overcount them. So, of course, this exclusion rule we just introduced by hand to match with the full theory. We didn't derive it directly from any bulk reasoning. The origin of the exclusion rule in the full many universe theory was geometrical. It came from this fact that we have the different z's in the correlation functions share the same psi of z states. However, it's tempting to take this no overcounting idea more seriously. We can ask, are there other theories described by this same effective model or version of it in which the exclusion rule arises because of the full theory views the cylinder and the corresponding diagonal piece of the dynamical boundaries as two descriptions of the same object, related by some sort of quantum equivalence or gauge equivalence or maybe a duality. I'm not sure what the right notion is. And this is reminiscent of some recent work by Eberhardt and Jafferis. So the SYK model provides a possible example of this. This is building on some ideas of Harlow and Jafferis. So in the SYK model, partition functions are typically averaged over the couplings J with some set of indices, Q indices here. So these J-averaged partition functions can be represented with a path integral over G sigma collective fields. So as an example, if we take two copies of Y, we have a 2x2 matrix of collective fields, same side fields and off diagonal fields, which we refer to as the LR fields. The G sigma collective fields are closely related to the JT gravity approximation of SYK. The double cone saddle point of the LR field plays the role of a space-time wormhole. So what happens when we don't average over the couplings in the SYK model? Well, if we don't average over the couplings and instead focus on a single choice, of course, partition functions factorize. However, we can still introduce these G sigma collective fields and then in principle integrate out the fermions. What this does is it adds a noisy term to the action, a noisy term which depends on the precise choice of couplings. So for two copies of Y, we may choose to introduce or not introduce the LR collective fields when we introduce the G and sigma fields. The result of the calculation is the same. These LR fields integrate to 1. So we can make an analogy. Computing with the LR fields or without them is analogous to calculating this 2-point function of Y's, or the 1-point function squared in JT gravity. The first computation, the 2-point function, has a fundamental wormhole plus off-diagonal corrections. That's like including the LR fields. The second computation, the 1-point function squared, is a manifest double sum, it's a double sum which manifestly factorizes with a potentially emergent wormhole. This is like computing without the LR fields. So this gives an example of an equivalence or between something like the wormhole and matched disconnected configurations. So how does this work? So the noisy term in the action depends on whether or not we include these LR fields. So if we do include the LR fields, do we see the diagonal plus off-diagonal structure that we've seen earlier, with configurations of the LR field playing the role of the diagonal sum, and the noisy terms in the action contributing something like these off-diagonal terms? Well, the model is difficult to control with exactly fixed couplings. One thing we can do is use small j perturbation theory as a tool. In this case, perturbative fluctuations of these LR fields sum up certain fermion diagrams where the flavor indices of the left and right fermions are matched. This is related to the fact that the LR field G is made out of matched fermions on the left and the right. However, it's difficult to connect this to the double cone saddle point because we're looking at this at weak coupling. To have some better control, we can approximately fix the couplings in a way which allows us to indirectly study these noisy terms using G and sigma saddle points like the double cone. So basically, we can just copy our procedure from JT gravity and work in an ensemble for which y is approximately fixed for an interval in the RAM. Approximate delta functions into the usual J average. So if we want to compute two y's with the couplings approximately fixed, we insert some tight Gaussians into the usual J average, which essentially project the ensemble onto J's which satisfy this. So here, this for delta small, this fixes y of t to be equal to y naught of t. And we can insert these for many different choices of time t. So once we've inserted these into the usual J average, we can expand out the exponential and introduce G sigma fields for these auxiliary copies of y of t. And because all of this is being done inside the usual J average, the resulting G sigma integrals are the conventional ones without these noisy terms in the action. So for appropriate observables and appropriate choices of approximate fixing, the many replica G sigma integral with the physical y's and these auxiliary y's can then be done by saddle point using the leading saddle point and this double cone saddle point. The result mirrors the calculation in JT gravity, but now with the double cone saddle point playing the role of the cylinder connecting different y's, and the auxiliary y's from these tight Gaussians playing the role of the state boundaries. So just as an aside, in practice in JT gravity, when we want to do this approximate fixing, we essentially do something like this by we insert these tight Gaussians into the usual average or in the no boundary state. So this very much similar to what we've done in JT gravity. So like in JT, we start out with many auxiliary boundaries or many state boundaries, but we can find an effective description for two y's with just two auxiliary boundaries added. So here on the right, I have the picture for JT gravity. If we have two y's, we have to add at most two auxiliary boundaries. In SYK, we don't have geometries per se, but what I've done is I've drawn some thermal circles for the two y's, or time circles, and time circles for the auxiliary y's. And the dotted lines connecting the different copies of the system represent the G fields. So these G left right couples the left system and the right system. This G connects the right system with the auxiliary system here. So now we can do something which is a little different than what we can do in JT gravity. We can further integrate out these extra auxiliary boundaries. So that would leave us with an action for just the physical G sigma fields for these left and right copies of this. This is going to be the action with the anticipated noisy terms for approximately fixed couplings. So essentially, these auxiliary boundaries induce these noisy terms. The advantage of doing things this way is that the effective description allows us to study how these noisy terms behave using the G sigma saddle points with the presence of these auxiliary boundaries. So how do things end up working? Well, if we don't introduce the LR fields, as we'd expect, the resulting noisy terms contribute a manifestly factorizing double sum. But if we do introduce the LR fields, the noisy terms that we get by integrating out these auxiliary boundaries give a purely off-diagonal contribution. The diagonal double cone contribution from the LR field is subtracted or excluded. So the punchline is that there's these two equivalent representations of the G sigma integral with the Euler fields and including the double cone, but with an exclusion rule, or without the Euler fields and including the corresponding diagonal noisy terms. Okay, so finally, we have some questions we can ask. How is this, the big question is basically, how is this relevant to conventional ADS-CFT? In this talk, we really focused on these simple models which are described by ensemble averages of systems. And then we were allowed to focus on one member of the ensemble. But how can any of these ideas be relevant to a system like Super Yang-Mills, for which there is not an obvious ensemble? What, in this case, would provide a microscopic realization of these dynamical boundaries? One possibility is that periodic fuzzball configurations or microstate geometries would play that role. But we'd also need a bulk explanation for the exclusion rule. So a related question to how does the exclusion rule work in this context has to do with the disk or the Euclidean black hole. In a full bulk description, is the black hole equivalent to some contributions of microstates? So maybe there's a choice between describing the black hole or describing the system by using the black hole geometry plus some corrections, or trading the black hole geometry for some subset of noisy corrections. Similarly to how we've traded this diagonal sum for a geometric thing, the cylinder. A case to look at is the tensionless string in ADS3, where Eberhardt found this sort of equivalence between the black hole and microstate contributions, as well as some indications of an equivalence between the wormhole and disconnected quantities. So in this case, it would be nice to understand a little bit more in detail how this works from the bulk point of view. Okay, so I believe that's it. Okay, yeah. Any questions?
Thank you very much, Phil. So, questions? You can raise your hand if you have any question there. Well, I don't see. There's a question. Go ahead.
Hi, Phil. I just want to ask about this exclusion rule. So is the background is that like naively, even when you put in this random boundary with the wave function big psi of b, you still somehow would have thought that the naive sum over geometries would have a cylinder in it?
Yeah. Yeah. There's
so what's the new rule?
From the bulk point of view, would there be some rule for like what's the rationale from the point of view of the bulk, not to include the cylinder as well? Your rationale could be that you want the answer to factorize, but that's maybe you want something that's a little bit more.
Well, maybe I was asking a pre-question, like why would you expect the cylinder to be there? So is the idea like in Merolf-Maxfield, in the Hartle-Hawking state, we connect up all the boundaries? So even here, like a priori, you want to connect up all the boundaries.
Yeah, that's a reason. There's some examples where the connected geometries are like saddle points. So for this time average spectral form factor, if you fix the energy, there's an actual saddle point, this double cone saddle point that acts like the cylinder. And we don't know the rules for the bulk theory, I guess, well enough to say definitively whether we should include that or not, but I think people are used to the idea that if there's a saddle point, it's reasonable
Right. I guess
to sum over it. Maybe there's some reason not to include it, like it's not on the right contour or something like that. And if you change the contour to include it, some other things come up.
Let me maybe ask it a little bit differently. So in Marov-Max fields, we have some set of rules, like we insert these boundary creating operators, and the choice of the third quantized Hilbert space dictates the geometries, right? Now you have this new object, this big psi of B. Could you just say what the rules you are using are with this big psi of B?
Oh,
what is the analogous
the rules with the big psi of B?
Yeah.
Yeah. So it's essentially what you were saying, that the rules, so the rules that we connect all the boundaries with any of the allowed geometries, we've gotten rid of all the higher genus things and surfaces with many boundaries. So we're just working with disks and cylinders. But for some set of boundaries, we sum up over all the surfaces which connect them. So that includes disks, cylinders, and cylinders with a dynamical boundary. So we've chosen that rule just because it's a simple rule for the sum over geometries, which is supposed to be similar to what happens in the full model. Does that answer your question? So maybe what you might think is if you have something like some microscopic origin of these dynamical boundaries, like instead of it being a random boundary, it's some solution of the bulk theory or something like that. That will be the natural bulk rule. So we've basically chosen that for that reason.
So I think Elena got disconnected. Raghu just says,
oh, okay.
Thank you. Yes. So somehow I became the host. Elena, if you connect back, just raise your hand and I'll give you back your sharing rights. But in the meantime, there's a question by Douglas. Go ahead, Douglas.
Hi, Phil. Could you go to, I think it's maybe slide 32, the one where you're talking about the yeah, this one. So when he says, so factorization here means factorization in this when delta is small, or?
Yeah, when delta is small. So like as an precise example, if you calculate we've worked in this approximate ensemble, this is approximately fixed ensemble. If you calculate the variance of y in that ensemble, it should be of order delta, which is small.
Okay, but somehow delta is not small enough that, like, if you pick the wrong kind of y naught of t, then the answer is 0 or something. Like.
Yeah. You have to be, so it's similar to JT gravity. You have to be a little bit careful with the y naughts that you pick. I didn't talk a lot about any of the caveats or whatever. Okay. This only works for some y naughts, but yeah.
Could you? Is it possible to explain how the exclusion arises on the next slide? That sounds interesting.
Oh, well, it's essentially like maybe the way to say it is so when you include these y boundaries, these auxiliary y boundaries, you're summing over basically some parameters attached to this. So like when you include these y boundaries, you have some like an integral over yeah, okay, maybe here's the way to say it is when we include these y boundaries, they come with an integral over some variable, let's say p. And it's the same for every, we have one integral over p, but every auxiliary boundary comes with a factor of p, and then there's a Gaussian integral in p. So what happens is when you have two auxiliary boundaries, the answer you get is integrated over P. And so you don't get with the answer for 2 copies of Y separately. It's like 2 copies of Y integrated over P. And that ends up, with the way things are set up, acting like the 2 copies of Y integrated over P separately, minus this correction term. It would probably take a lot longer to explain why I introduce P. It's related to the fact that the calculation is a lot easier if you re-express this Gaussian as but with a Fourier transform. That's the Fourier transform variables at P. But I think it might take me a lot longer to get into any more detail. I don't have a good way to explain off the top of my head.
Okay, yeah, thank you. Thanks.
Okay, we have one more question. Go ahead, Shenbin.
Hi, Phil. May I ask, here you're focusing on this ending on this random boundary, but is there a chance that it's actually coming from some random bulk interactions? Because SYK there's matter field and they somehow have this random interactions in the bulk.
Well, so there's like 2 sort of very different contributions to the variance of Y in SYK. One is suppressed by a power of like n to the q, and one is exponentially suppressed in n.
Yes.
The second one, the exponentially suppressed one, comes from this G sigma saddle point, and that looks like a cylinder geometry.
Mm-hmm.
So we're focusing on things that are related to that, because these other things with the 1 over n to the q suppressed variance, they sort of disappear at these times on the ramp. They decay in time.
But they in the SYK they are coming from averaging over the J, the random coupling, right? So
yeah, we don't understand in detail really like a good way to separate those 2 things without we don't understand have a very good picture of how they're separated. It's just in practice you can get rid of those
mm-hmm.
those sorts of fluctuations, which do look like more like the random bulk interactions, by working at these later times.
Maybe they are the trends that they are actually related, because in SYK they have only one variable there, your average.
Yeah, this is maybe related to the fact that like the fact that there's only n to the q different couplings. Using these saddle points, you get an answer which looks like what you'd get from JT gravity. And there in JT gravity, you have like e to the n, your e to the s random variables. In SYK, we only have n to the q random variables. And related to that, this approximation with the disks and the cylinders breaks down in these eigenstates. There's some signs that it breaks down if you try to fix more than like n to the q different times, or fix y different times. So if you try to focus on too closely on a specific choice of y, those effects from these, we think those effects from these 1 over n to the q suppressed terms become large and invalidate the approximation. And so the picture is different. But it's like when you're not sensitive to the fact that you only have n to the q different couplings instead of e to the n, you can just use these simple saddle points to describe everything.
Yeah, I saw one said in the chat that you can take q square scale with square root of n to suppress the contributions. I'm not sure. Yeah. I see. Thank you.
Yeah, so I have a question, Phil. I wanted to make sure I understood something about the scales at the beginning. So at some point, you draw the erratic signal and you say you don't capture all of it, but you capture some sort of gross features of the erratic signal.
It's like what we can do is calculate just up. So one, there's up to a certain time scale. It's not the whole ramp. The details of time related to, we choose an error in defining these approximate eigenstates. The size of the errors, so the variance of this signal, if we do something like time averaging, is like of order 1, say. We choose an error in the size of this approximate eigenstate, which is much smaller than 1. And so what we can do is we can calculate this for this time range, which is set by the size of that error. We can calculate the function to within an error of size delta, which is much smaller than 1.
I see. I see. Okay. Yeah. Thanks.
Okay. If there are no more questions, we should thank Phil again. Thank you, Phil. And we'll reconvene in 7 minutes.